Okay, we finally made it after several months and many videos. We've reached the fundamental theorem of calculus part 2. You may have also noticed that we have not yet discussed the fundamental theorem of calculus part 1. There is a reason for that. Part 2 is better and also just something that we'll probably use more. So we'll come back to the fundamental theorem of calculus part 1 later if we have time. Spoiler, we will not have time. But I've included part 1 in the notes if you want to read through it and get a sense of what it says. We are going to focus on part 2. So before we actually get into the statement of this very important theorem, I just want to remind you of the two different types of notation that I've introduced you to in chapter 4. The first had to do with general antiderivatives, right? So remember, when we had this integral symbol, we had this sort of stretched out S symbol, it's an integral symbol of a function f of x dx. This represents the general antiderivative of the function f of x. Right, we also call this an indefinite integral. Okay, and so when we write the indefinite integral of f of x with respect to x, what this really represents is a function, right? It's some function big f of x, right? Some other function big f of x, where this big f of x is the antiderivative or general antiderivative of little f of x. So big f of x has this property that if you take the derivative of big F, you get back that little f. So big f of x prime should be equal to little f of x, right? So this, without having numbers on the top and the bottom, this just represents the function, which is an antiderivative of little f of x, plus c at the end, which makes it a general antiderivative, right? Because any addition of a constant at the end is still going to make it an antiderivative. Now we can compare this with what we talked about in the last video, which we called the definite integral. So the definite integral, the notation looks a lot like indefinite integral notation, but now we have an a and a b at the top and the bottom, and those a and b's are real numbers. And so this represents the area between a curve in the x-axis over a particular interval of x values, right? So this integral, if this is the function f of x, and this is a and b marked on the x-axis, this here represents the area between the curve and the x-axis over that interval. So it represents this exact area right here. All right, so this notation is going to denote some real number, because area has to be a number. Maybe it's positive, maybe it's 0. It could be that the area, if there's 0 area there. It could even be negative because we consider it to be signed area. If your curve dipped below the x-axis, we consider that to be negative area. But in particular, this is a number, right? Whatever this is, it should be some real number, as opposed to the indefinite integral, which is a function, okay? And so this is the exact area, signed area, between a curve f of x and the x-axis. Okay, and you'll recall that to calculate this, well, we sort of just had to hope for the best, that our function here was like a straight line, so that the area turned into maybe a rectangle or a trapezoid or a triangle or something just that we know how to take the area of. Maybe even a circle. If the function was a circle, we'd be able to take the area as well. But otherwise, all we really know how to do so far is to estimate that area using Riemann sums, right? By breaking it up into a bunch of little rectangles and adding up the area of each rectangle. And so it seems a little bizarre at first that we would use the same notation for both of these things, right? The indefinite integral, without having a number at the top and the bottom, represents an antiderivative function. And the definite integral, with numbers on the top and the bottom, with these bounds here, represents the area under a curve. Why are we using basically the same notation to mean two things that seem completely different from each other? Well, it turns out that they're not completely different to each other, that the fundamental theorem of calculus links these two things to each other in a very concrete and very useful way, which is going to allow us to compute the area under any curve without actually using Riemann sums, without having to deal with those boxes or even limits of those boxes. Right? It gives us a really nice concrete way of doing it. So here it is. This is the big reveal, fundamental theorem of calculus part 2. It says assume f of x is continuous on the interval from a to b. If big F of x is an antiderivative of little f of x, right? So if big F of x is the general antiderivative of some function little f of x, then we can compute this definite integral from a to b of f of x dx by taking the antiderivative, big F of x, evaluating it at the right endpoint, minus evaluating that antiderivative at the left endpoint. This is what the fundamental theorem of calculus says. So just to be clear what we mean here, here's your function, f of x, from a to b. Okay, and we're trying to compute this area. Right, remember, that's what the right-hand side is representing. It represents the area between a curve and the x-axis over the interval from a to b. This is telling us we don't have to deal with those crazy Riemann sums. We don't even have to try to figure out, some shape that's roughly like this to estimate it. We can find this exact area by taking the antiderivative of this function, right, going backwards and taking the antiderivative, and then just plugging in the two endpoints, b and a, and subtracting big F of b minus big F of a. So it's the antiderivative evaluated at b minus the antiderivative evaluated at a. This is so nice. This is so clean. It's not hard for us to do antiderivatives, at least of the functions that we've been dealing with so far, things like polynomials and basic trig functions. So this is a really easy way of finding this area. So let's do some examples to see how this works. We're not going to prove this theorem here. You'll prove this at some point, probably analysis, maybe Calc 2. But we'll just do a couple of examples to see how this works. So I'm going to bring us back to the very first example that I did at the beginning of section 4.2. I said, how would you find the area under this curve x squared, which is a parabola, right? X squared looks like this, over the interval from 0 to 3, right? 0 to 3 would be this area right here. Okay, that's what this represents. It's saying find the area between the curve f of x equals x squared and the x-axis over the interval from 0 to 3. That's the first question that I asked. I didn't write it like that, but that's the question that I asked. And we had said at the time that we can maybe just estimate it by like turning this into a triangle, but that would be an overestimation because it would include some area kind of above the curve right here. Well, the fundamental theorem of calculus tells us all I need to do is take the antiderivative of x squared and then evaluate it at 3, evaluate it at 0, and subtract. And that's going to give me the exact area that I'm looking for. Okay, so let's see, we've got, well, maybe what we should do is first, step 1, find the general antiderivative of x squared. Right, so the antiderivative of x squared dx, right, without bounds means just find the antiderivative function. And we had learned that to find the general antiderivative using the power rule, you add 1 to the exponent and then multiply by 1 over the new exponent. So the antiderivative of x squared is 1/3 x cubed. Then we put a plus c at the end because in general an antiderivative can have any constant added at the end. As long as this is a constant here, when you take the derivative of 1/3 x cubed plus a constant, you get x squared, as desired. So now step 2 is to take this antiderivative and plug in 3 and plug in 0 and subtract. Now just as a little bit of notation here, if we wanted to compute, here let's call this our big F of x, right? We use big F to represent the antiderivative. So if we wanted to compute big F of 3, minus big F of 0, right? We have a shorthand for that, which is just to say big F of x, right, the antiderivative function of x. Then we draw this line here, and at the top we write 3 and 0. It's just shorthand notation. That means plug in 3, then plug in 0, and then subtract. F of 3 minus F of 0. Big F of 3 minus big F of 0 is what I mean. So this is common shorthand that you use when you're doing derivatives, because you're always finding an antiderivative, then plugging in the endpoints and subtracting. So here's some shorthand that we'll use for that. All right, so let's actually do that then. If I plugged in 3 into this function, so here, let's write it here. So big F of x evaluated at 3 minus evaluated at 0 is going to give me, all right, big F of 3 would be 1/3 times 3 cubed plus a constant, right? That's the F of 3 term. I'll put it in brackets just to keep it separate. And I'm going to subtract big F of 0. Okay, big F of 0 would be 1/3 times 0 cubed plus that same constant, whatever it is. Okay, so this turns into, let's see, 3 cubed is 27. 27 times a third would just be 9. So it'd be 9 plus a constant minus 0 plus a constant. Okay, so just minus c. Ah, look what happens. The c's cancel out. And we're just left with 9. 9 is going to be the area under the curve. That's it, right? It's just as simple as that. That exact area is 9, which is a little bit surprising that this sort of curved triangular-ish looking thing has an exact area of 90, but that's what it is according to the fundamental theorem of calculus. I want to point out one thing. When we found the general antiderivative, we had a plus c here, and this plus c, remember, is just an arbitrary constant. It could be anything. But when we evaluated that antiderivative at 3 and at 0, and subtracted, the plus c and the plus c in f of 3 and the plus c in f of 0, they're going to cancel each other out in the end because we're subtracting c and then minus that same c later. And so the c's sort of, you don't really have to worry about them when you're computing definite integrals, right? If you're just finding a general antiderivative, you do need the plus c, but when you're computing a definite integral, those c's are going to cancel each other out and you don't really have to worry about them. Okay, so let's try another example. This time we're going to find the definite integral between 1 and 4 of the function 8x cubed plus 2. All right, so what does this look like? I don't really know. Something like this, right? Some cubic function that's been scaled a little and shifted up too. So it looks something like this. Between 1 and, well, maybe I'll do this. 1, 2, 3, 4, so I can actually fit it all in my picture. Okay. So we're looking for this area here, right? And so what we can do is apply the fundamental theorem of calculus. So step 1, find the antiderivative of this function here. So the general antiderivative of 8x cubed plus 2 with respect to x, right, we just have to use the power rule again. So we add 1 to the exponent, so it'd be x to the 4th, and then we divide the coefficient by the new exponent. So we take the old coefficient and divide it by the new coefficient, which is 4. Right, plus the antiderivative of 2 would be 2x, and we have a plus c. Cat's making a lot of noise in the background here. I don't know if you can hear, but I'm very sorry. She is the living worst. All right, so this is our antiderivative function. Call it big F of x. And so step 2 is just to take that function big F of x and evaluate it at the two endpoints, at 4 and at 1. Remember, this notation means just subtract. Big F of 4 minus big F of 1. Okay, so what's this going to be equal to? Well, this function is probably easier to write it as 8 over 4 would be 2x to the 4th plus 2x plus c. And remember, we don't really have to worry about the plus c when we're doing definite integrals because they'll cancel each other out. So I'm just plugging in 4 into this function, then I'm plugging in 1 into this function and subtracting. So first I'll do big F of 4, so it's 2 times 4 to the 4th power plus 2 times 4 minus, now I'm going to evaluate this function at 1. 2 times 1 to the 4th power plus 2 times 1. All right, so what does this end up being? Oof, I don't know. Would be 4 times 4 times 4 times 4 would be like 16 times 16. So I should have done some scratch work ahead of time. Oh yeah, 56, 256. Then I have to multiply that by 2. Oh boy. 512. Okay, plus 2 times 4 is 8. And then I'm going to subtract 2 times 1 plus 2. So subtract, this is just 4 when I simplify this. So this is like 512 plus 8 minus 4, which is 520 minus 4 would be 516. Units squared, whatever your units is, that's the area of this region. Doesn't look like that much more area than this, but my scale is definitely very off here. Okay, so this is another example with polynomials, but let's do an example with more interesting functions. Cat is so loud. All right, let's do another example. This time we want to find the definite integral from 1 to 9 of 1 over 2x dx. What does this look like? I mean, I can try to guess. I know that 1 over x looks something like this, and this has just been scaled a little bit, 1 over 2x, so it'll still look roughly like this. And I want the definite integral from 1 to 9. So I want this area here roughly. Okay. All right, so I need to apply the fundamental theorem of calculus, which means I need to take the antiderivative of this function. One thing to note, it's useful right off the bat because I know I'm going to have to take the general antiderivative to rewrite 1 over 2x as 1/2 times 1 over x dx. Right? We can see that these are the same functions, but this is just a scalar times 1 over x. And I know the antiderivative of 1 over x is log of x, or ln of x. All right, so I just did that to help me remember how to do the antiderivative. Step 1 is to take the general antiderivative. So we're going to take the antiderivative of 1/2 times 1 over x dx. I know that that's just that same scalar 1/2 times the antiderivative of 1 over x, which is ln of x. And we put absolute value bars around it just so that the domains are the same, plus c. Okay, now call this your antiderivative big F of x. Step 2 is to take that antiderivative big F of x, evaluate it at 9, evaluate it at 1, and subtract. Right, so I need to find big F of 9 minus big F of 1. And again, the plus c doesn't really matter when we're doing a definite integral because they'll cancel each other out. So this is just as simple as saying 1/2 times ln of the absolute value of 9, which is just 9, minus 1/2 times the absolute value of, or ln of the absolute value of 1, which is 1. Okay, so it's just 1/2 times ln of 9 minus 1/2 times ln of 1. What is the natural log of 1? Well, that's 0, because e to the 0th power is equal to 1. So ln of 1 is 0. So this whole term goes away, and we're just left with 1/2 times the natural log of 9. Units squared. That's how much area is under the curve. Okay, just a couple more examples. Let's say we wanted to compute the antiderivative from -1 to 8 of 5 times the cube root of x dx. Just like before, I need the antiderivative of 5 times the cube root of x. So it's going to be useful. I guess I could try to sketch this if I wanted to, but I don't really super know what this looks like. Probably something like this. Right? Something roughly like that. And I'm going from -1 to 8 here. Right? So this area under the curve, remember, it's signed area, so it's going to include a little bit of negative area on the left-hand side to the left of the y-axis, and then a bunch of positive area to the right. But it doesn't even really matter. You don't have to worry about that because the fundamental theorem of calculus is still just going to tell you just take the antiderivative of this, evaluate it at 8, evaluate it at -1, and subtract the 2. So start by taking the antiderivative. Okay, it's going to be useful. I can apply the power rule if I rewrite this as 5x to the 1/3 power. Okay, so step 1, find the antiderivative of 5x to the 1/3 dx. So I need to add 1 to my exponent. All right, 1/3 plus 3/3 would be 4/3. And then I need to multiply by 1 over the new exponent. So 1 over 4/3, which is like 3/4. And oh, we still have a coefficient of 5 out here. Okay, I've done a bad job of writing this, but this is 5 times 3/4 times x to the 4/3 plus a constant. Okay, the constant's not going to matter when we do the definite integral. But step 2, if this is my antiderivative function, and it's probably useful to just rewrite this as 5 times 3 would be 15/4 x to the 4/3. Let's see. Okay, step 2 is to take that antiderivative and evaluate it at the endpoints, 8 and -1. Okay, so I plug in 8. Bean, chill. Sorry, the cat is terrible. All right, 15/4 times 8 to the 4/3 power. The plus c is going to cancel out, so I can ignore it. Minus 15/4 times -1 to the 4/3 power. Okay, how do we actually compute this though? We have to be careful. So one thing to consider is we could rewrite this as 15/4 times, right, a 1/3 power would be cubed root. So we could say cubed root of 8 to the 4th power, right? Or minus 15/4 times the cubed root of -1 to the 4th power. Okay, and this is going to be, well, the cubed root of 8 is just 2, because 2 times 2 times 2 is 8. So this is 2 to the 4th power, which is 16. So this is 15/4 times 16 minus 15/4 times the cube root of -1 is -1, and -1 to the 4th power is just 1. I'm running out of space a little bit here. These 4's will cancel, so we're left with 15 times 4, which is 60 minus 15 over 4. Okay, whatever that is. You don't have to simplify that further than that. This is fine. Okay, or write it as a fraction if you want. I don't care. But this is by the fundamental theorem of calculus part 2 as well. And now I have one last example to do. This is a trig function. So let's say we wanted to compute the area underneath the curve of the function sine of x between 0 and pi. All right, from 0 to pi, sine of x just looks like this, right? After that, it's going to keep going, and over here, it's going to keep going. But between 0 and pi, this is what the graph looks like. Almost looks like it might be a half circle, but no, I don't think it is. Okay, so how do we do this? How do we find this area here? It's a fundamental theorem of calculus, of course. So let's see, we've got step 1, find the antiderivative of sine of x dx. That's just negative cosine, right? It's not just cosine because the derivative of cosine would be negative sine. So if we want a positive sign here, we have to put a negative sign over here. All right, so that's my antiderivative function, big F of x. Step 2 is to take that antiderivative, big F of x, and evaluate it at pi, evaluate it at 0, and subtract. So this would be, oh, this isn't a dx, my bad, this is a plus c. Doesn't matter, the plus c is going to go away anyway. Okay, so this is negative cosine of pi, right, that's big F of pi, minus negative cosine of 0. Okay, so what is negative cosine of pi? Well, cosine of pi, if we think about the unit circle, pi degrees is over here, cosine's the x-coordinate, so cosine of pi would be -1. So negative cosine of pi would be -1, or +1. Okay, minus negative cosine of 0. Cosine of 0 is all the way over here. It's the x-coordinate, so it would be 1, so it's minus negative of 1. So a negative would be a positive 1 plus a positive 1. This area is 2. That's kind of a fun fact, that the area underneath the curve between 0 and pi of the function sine of x is 2 units squared. It goes all the way up to 1 here, so that's kind of fun. All right, in the next video, we'll talk about sort of using some properties of the sine function and other trig functions to do some shortcuts of definite integrals, as well as to try to find the area between two curves.